Okay, thank you. So thanks for the opportunity to give this talk, and yeah, thanks for organizing this long program. Unfortunately, I will not be able to hear for most of it, but I enjoyed like last week, and then till tomorrow I'll be here. So yeah, so this talk is going to be about dynamical quantum error correction and non-invertible symmetries, and it's based on this paper with Nat and Adar Sharon. So because we have like a mixed audience, maybe I can start with uh, explaining how the talk will progress. So I will first explain this part here about quantum error correction. Then I will go into explaining what dynamical means in this context. And then I will explain some aspects of non-invertible symmetries. And hopefully we will get to this arrow here, which will be the connection between the two. So maybe a simple example for error correction would be that I guess all of us are old enough to know a compact disc CD, and when we first get a CD, it's all shiny and everything, and then with time you get all these scratches on the CD, and then you insert it into your computer and it still works well, and that's because there are error correcting codes in the reader of the CD which is doing the work for you to make sure the data is not, you can recover the data even if you have all these scratches on the CD. So that is classical error correction, which is heavily used in everything that we do. But now quantum error correction is the quantum version of it, where you devise certain methods to detect and correct errors when you store information in quantum devices. So assume some quantum computer where you have stored information, but there's environment attacking the system, and then you may make some mistakes, and so there's systematic errors and non-systematic errors. You want to detect if there are errors and correct them. So quantum error correcting codes are used for that, and I will give like a very general definition of that. Basically, what you start with in a description of a quantum error correcting code. So I will start with like 1. So what you start with is a Hilbert space. And we choose a particular subspace of this Hilbert space. So this is why I'm being very general in this context. So you choose a subspace C of this Hilbert space, and you write this Hilbert space as some direct sum, let's say. So all the states in this subspace and all the states which are like orthogonal to this subspace. And there are two maps or operations which are crucial in the context of quantum error correction. And one of them, let me just call it L, it's some map which maps states in C to C. And the other map which is relevant in our discussion is something that maps C to C orthogonal. So there are these two maps which are important. So anytime you have a Hilbert space, you can choose a subspace and study these two types of maps. So it's quite general. So let me try to give a outline of, obviously this can show up in many places. So let me try to give an outline of where this interesting structure shows up and where people have studied it in various contexts. So let me consider some kind of table. Okay, so let me, for H, I have this C here, I have the L and E, and this is the theorist or experimentalist. Now suppose you are a quantum information theorist, or let me put mathematician along with quantum information theorist. I don't know if it's correct, but let's me go ahead with that. In this case, this H is a Hilbert space. It's a finite dimensional Hilbert space of some qubits, physical qubits in your lab, let's say. So physical qubits. Okay. Now C is some subspace of the physical qubits, often called logical qubits. This is where you are storing your information. And L is a map from C to C. So it's actually a map on your logical information. So let me just call it a logical gate, just roughly. So it's a map that acts on your logical information and transforms it in some way. But E is something that takes you away from the subspace. So I'm just calling it E because it is, you can think of it as an error. So you want your information in the subspace, but an error or a detectable error, let's say, is something that kicks you outside the subspace, and then there are methods to detect this and come back to the subspace. Yeah, so I will consider L, which is unitary, and E, which is like Hermitian. I just write down some basis. I will eventually commit to polygroups and polymatrices. Yeah. So this is a QI/math description where you have these names for these. But suppose you are a condensed matter physicist, then H will be a Hilbert space of a lattice model, let's say. So let's consider some gap lattice model, and I consider the Hilbert space of these of this model, and that is H for me. And in this case, C is the ground states. So now you have some more physical interpretation for what C is. So you have this full Hilbert space of your model. C is the ground state, and now L can be thought of as symmetries of ground states, and then E is taking you away from the ground state, so it's an excitation. So E stands for both error and excitation. So this is what a condensed matter physicist would think of, closely related. Now suppose you are a high energy physicist, okay. So this is maybe even much less thought about, maybe. Yeah. Yeah. Yeah, usually you think about, well, it depends, but usually you think of it can be unitary only on the ground states also. Maybe you implement this unitary by acting with the non-invertible operators on the full Hilbert space. That is possible. But usually people consider some unitaries acting on the full Hilbert space, which acts on as a unitary on the subspace. Yeah. Okay. So if you're a high-energy physicist, let me take H to be the UV Hilbert space. Now you are in a much wider world. You have an infinite dimensional Hilbert space. You have the UV Hilbert space. C can be thought of, if you want, this is like a particular realization of this, because this is very general. You can think of it in various scenarios. This is the image of your RG flow. So this is like it's not the IR Hilbert space, but this is like the states in the IR that's arrived from the UV. So this is like the Hilbert space of the IR theory, which is kind of sitting inside the UV degrees of freedom. So many of the UV degrees of freedom you don't see. So you are interpreting this as like a subspace of the UV Hilbert space. And L now is like a symmetries in IR. And E can be thought of as some deformation away from some fixed point. So there are various aspects. So there are various some groups which study these error correction type properties of RG flows, try to interpret the IR Hilbert space as a subspace, and try to study whether you can use ideas in error correction to study formal properties of RG flows. Yeah, they could be accidental. Yeah. Yes, I'm still thinking of it as a logical gate. Yeah.
C is a subset of the IR Hilbert space, right? Like FRG.
That's right.
So should L really, to be pedantic?
No, sorry. Yeah, so maybe I should, well, maybe I should think about these symmetries as symmetries which are preserved in the RG flow. Maybe that's better. Yeah, because I want to act on the UV, and that should give me some action on on its image in the IR. Maybe that's better. Yeah, so I'm not completely sure about this interpretation. I haven't explored more the energy physics side of interpreting quantum mechanical writing codes. But as long as you are as long as you are moving away from this particular IR Hilbert space, you just call it E. This E map is basically just taking you away from this particular subspace. Yeah. So right. So and then finally we have quantum gravity. So if you do ADS-CFT, again this shows up, right? If you do ADS-CFT, really formally you think of an isomorphism between the CFT Hilbert space and the bulk Hilbert space. But often you are interested in the bulk you fix a background in the bulk and you look at excitations above that background. So you really don't have an isomorphism anymore between the boundary Hilbert space and the bulk Hilbert space. The Hilbert space that describes the bulk that you want about a fixed background is actually like a subspace of the CFT Hilbert space, because the CFT Hilbert space is supposed to know about everything in the bulk. So now H is like HCFT, and this is like H bulk, but for some semi-classical theory. So I'm looking at some quantizing about some background, and I have some states, and it captures only some part of the CFT Hilbert space. And here I have some symmetries of this, symmetries of H bulk. And a fancy way to say what E is like black holes. You just suddenly go to some high energy description. You go away from this bulk description. So E is, let me just call it like black holes, but because you are studying some empty ADS or some slightly curved bulk, and then you're studying states above that, and this is like high energy excitation. Okay, so so this is just to make contact with people in the audience doing different things, but really yeah, so this is the main structure, and the main ingredients will be the C, L, and E maps. So choice of a subspace and this L and E. Okay, I'll keep this here. Yeah, so let me, okay, so our focus will be very specific. It will be so for me I will just choose H to be Hilbert space of n qubits. So a bunch of two-dimensional Hilbert space, tensor product of a bunch of two-dimensional Hilbert spaces, and I will choose the subspace C. So there are various ways to choose a subspace, but a particular way in which I will choose a subspace is by assuming that the subspace is a +1 eigenspace of some group called S, which is a subgroup of the Pauli group. So what do I mean by the Pauli group? I have n qubits, and I have like the Pauli matrices X, Z, Y, and identity acting on each qubit, and I just take a tensor product across all the n qubits, and I get a Pauli group acting on n qubits. This is a non-abelian group. I choose a abelian subgroup, and I look at the +1 eigenspace of that subgroup, and I choose C to be the +1 eigenspace of that subgroup. Okay, so this is how I want to describe C as. It's not an arbitrary subspace. I am defining subspace through the +1 eigenspace of some operator S. It's a subgroup of the Pauli group. This is a setting now. It's invariant into the group, yeah. Okay, so before going into the general descriptions of what is an error, what are the logicals and things like that, I'll straight away just give an example, because that will be the easiest way to understand the setting. Yeah, S should be commutative to have a well-defined +1 eigenspace. Yeah. Right. So let me give an example. So this example will use 4 qubits. Okay. So we have a Hilbert space which is 16 dimensional. And we choose a subspace, and the subspace is chosen by choosing the group S to be generated by two operators. One is just x, 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 the other one is just z, 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 z. So these two, this is x acting on each of the 4 qubits, this is z acting on each of the 4 qubits. I choose the abelian subgroup of the polygroup to be this particular group generated by xxxx and zzz. This defines for me a subspace of this Hilbert space. Okay. So I look at the +1 eigenspace of this group. So let me write down explicitly. So I get 4 states +1 1 1 1. So this is just a label that I'm giving for this combination of states of the original Hilbert space. 0 0 1 1 plus 1 1 0 0. Okay, so I'm not normalizing things carefully, but these combinations of states are invariant under the group. So this defines a basis of states for the subspace determined by this S. Okay, so basically you have 2 qubits. So the logical space is 2 qubits, but the physical space is 4 qubits. Okay, what is the benefit of using the subspace compared to using the original qubits? Yeah. This is a toric code, indeed, yes. This is a special instance of the toric code. So it's a Z2 gauge theory, NDIR basically, but it's just literally the toric code with only 4 physical qubits. Yeah. And what is the benefit of doing this? You put the information in these states, and suppose there's an error. What is an error? So you can consider an error operator which is of the form something like IX11. So this is an error that can happen, or that can act on your qubits. But if there is an action of this on your logical qubits, this takes you away from the subspace, because this operator doesn't commute with this one. So if this error happens, you are away from the subspace. You can detect that this error happened by measuring this operator. You are in the +1 eigenspace of ZZZZ, but if this happened, you will be in the -1. You will get -1 as a measurement outcome. So by measuring these operators, you know whether an error occurred or not, and based on that you correct. So you can detect an error. Correction is another issue, but at least you can detect errors based on which operators anti-commutes with these stabilizer elements. Okay, so anytime you have a 1 qubit error, an error acting on a single qubit, you can always detect it because it anti-commutes with at least one of these guys. So you always detect that there's an error. So that is the benefit of this simple example. Okay, so how does so let me be a bit more precise as to how you detect the error. So at time t1, you measure these operators xxxx and zzz, and you get some measurement outcomes. Okay, you get measurement outcomes. So let me just call it the outcome to be this. So these are the measurement outcomes. These are some ±1 eigenvalue of the operator. You get this outcome at time t1. Suppose you start off your life in the subspace, these measurement outcomes should be +1. But let me not assume that. Let me just get the outcome, whatever they are. At time t equals 2, I measure them again. And I get outcomes for that. So how do you detect the existence of an error? If there was no error, you are still in that subspace. So the measurement outcome here should agree with the measurement outcome here at time t. Sorry, yeah, for these indeed. Yeah. So if this was +1, this would be +1. If this was +1, this would be +1. If this was -1, this would be -1. So what is the criterion that should be satisfied if there is no error? it is this equation that you write down, which is simply if you have O1, so let me just replace at time t, you have at measurement at time t of xxxx, this should agree with measurement at time t plus 1 xxxx, and similarly for zzz, okay, for zzz. So at each time interval you keep on measuring this xxx and zzz, and you keep getting the same outcome, and at some point you get in -1 or something that deviates from this, that violates this equality, then you know an error occurred between time t and t plus 1. So really you have this process where you keep on measuring these operators to make sure you detect errors at any time and you correct them. So you have to keep on measuring these operators to detect errors. Okay, so this is the mechanism. Okay. Questions on this example? So yeah, so what are some limitations of this or undesirable properties of this setting? So some limitations. Yeah, so logicals are by definition things that commute with xxx and zzz. So any operator you write down which commutes with both. So if you have like a 2-qubit operation, you know, such that it commutes with both xxx and zzz, you are guaranteed that when it acts on the ground states, it will just map to some combination of that ground states. Those four states, I mean. So that is a logical. Yeah, so in fact you can write down, like there are 2 qubits, so you can write down x, z, y for these 2 qubits. So you get, for example, you get the poly group on 2 qubits. All of them are logicals acting on the subspace. Yeah, there are some trivially acting ones like xxx itself commutes with this, but it doesn't act on anything. It's a +1 eigenspace of that operator. So you have to mod out by that. But if you have something like xx11, this is a logical, right? It commutes with both. So when it acts on one of those states, you just get the other state. When it acts on this 0, 0, these get mapped to, which one does it get mapped to? Maybe let's say up to permutation. Oh, there should be a 0, 0, 1, 1 here. Okay, yeah. So operators like this, which commute with both, are the logicals. But this is actually the same as 1, 1, xx, as long as the subspace is concerned, because these two are related by multiplying with xxxs, but xxxs doesn't act non-trivially. So these are identified. So there is a lot of redundancy in how you implement a logical, but these are the operators like this are the logical. Okay. So so more and more complicated versions of this. In fact, this is an example of toric code, and toric code which is defined usually on a torus, but with a flat version of it with appropriate boundary conditions, is the most prominent error correcting code that is being studied and trying to build it in the lab, I guess, to correct errors, hopefully correct errors in a future quantum computer. So what are some limitations though of this setting? Okay. 4-qubit measurements. So in order to do this error correction, we have to keep measuring these operators xxxx and zzz. This is measuring 4 qubits. It's a 4-qubit operator. You have to keep measuring in your lab. Let's say you have to be able to measure these, and these measurement outcomes should not have error. Let me go to the ideal case where these measurement outcomes do not have error. So you need to have a lab setting where these outcomes do not have error. So you should be able to do the 4-qubit measurements very well in your lab. However, in most settings it is desirable if you can get 2-qubit measurements or 1-qubit measurements. They would be the easiest to implement because you have to only take care of 2 qubits at any time. This example involves 4 qubits, and most of the codes that are studied involves even more qubits. in the stabilizer group, this group S. So it's okay, the 4 qubit measurement is not too bad, but ideally maybe we would like 2 qubit measurements and 1 qubit measurements. So that is one limitation that in this setting. What is 2? As I said, you would like to implement these logical gates on your encoded qubits, and you should not, you want to realize an arbitrary operation on the logical gates. You should be able to do universal quantum computation. Any unitary, you should be able to act on the logical gates. And you should act on the logical gates in a logical states in a local way. You should not implement this logical by acting on multiple qubits together, because if there is an error in your implementation of your logical, it will create a lot of errors. So basically the logical, which you think of as a symmetry of your ground states, the way in which you act, it should be very local. It should be a product of local operators. However, there is a tension between implementing a logical locally versus error correction property of the code. So there's a theorem which is, so Easton-Kennel or Easton-Nil, I'm not sure yet, but there's a theorem which tells us that logicals acting without creating, so let me just paraphrase the theorem, but logical acting without creating too many errors form a finite group. So you devise a criterion for what it means for logicals to act without creating too many errors, and you check, can I implement some SU2 or SUN of unitaries on these logical qubits? You can show that you cannot. There's only a finite group of logicals that you can implement using these. I haven't made precise what it means to not create too many errors, but it's called transversal gates, if you know the word transversal. So this is the problem now, because you want to implement everything in a fault tolerant way, in a way that doesn't create too many errors, but you can only implement a finite subgroup, which is far from the continuous group that you want. So this theorem assumes that you are on a fixed error correcting code. This is where the assumption comes in of this theorem. For a fixed code, this theorem applies, and you cannot implement anything more than a finite group. And also in this example, we see there are 4 qubit measurements. We would like to reduce the number of measurements. So these are some limitations, and we would like to devise a method which kind of circumvents these limitations. And maybe most of the techniques that people invent in quantum error correction is to kind of circumvent this second theorem. You want to find ways to kind of go around this theorem to implement a universal gate set. Yeah. Yeah, so for example, if the logical X, which is acting on this subspace, is just given by, if it is just given by acting with the logical X on each physical qubit, this is a transversal gate, because if there is an error in implementing X, for example, in 1 qubit, it will create an error on 1 qubit, but your code can correct that error. So creating errors in one single qubit is okay, but if you have an implementation of a logical X which uses too many qubits, physical qubits, such that it creates many errors when you do it, then the errors will increase uncontrollably. You cannot correct them with your code. So transversal really means that the logical operator, the logical unitary, is a combination of tensor product of unitaries acting on each qubit. That's what it means basically. Yeah. So this ensures that the whole operation is made up of acting on each qubit individually. So if there is an error, it only creates an error on 1 qubit. That's all it means. Yeah. 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 So in this, I was just giving you an example. It's not really this case. Yeah.
This definition or this statement.
Yeah.
Because the logical gates
function that doesn't go out from the code subspace.
That's right. Yeah. Yeah, but the thing is, logical gates is so always you're acting with something on the physical qubits. That's what you have in the lab. So always the full action is on your full Hilbert space. But when you restrict that action on the subspace, it should only take you to the subspace. That is the precise definition of a logical, because all you have in the lab is the physical qubits. So you act with some operation on the full Hilbert space. When you restrict that action on the subspace C, the outcome should be in C. That's the definition of a logical. If the restriction of that action to C gives you outcomes outside C, it's not a logical. Yeah.
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 Maybe I understand your meaning, but
yeah, logicals itself will not. I am happy to discuss it more, but logicals itself will not play a role in this talk. So yeah. What do you mean? Yeah. So it is not something that you see in the math, right? In the sense that if your gate is the way you implement the gate is ideal, it will map C to C. But the way you actually implement in the lab may be like you want to implement X, but you implemented X times something, which will take you outside the subspace. So you are leaving room for this like lack of precision in the way you realize this logical. So if in the math side you say, oh, this is a logical, so it should map C to C. But you want to implement a logical, but actually what you implemented is the logical that you want times some error. And that error is the one that you will kick you outside C. Yeah. So, but at the end of the day, at the physical qubit level, you can still answer the question, does it create an error in a single qubit or not? Does it act in an undesirable way on a single qubit or not? That is why the error comes in. Okay. So yeah, I just want to highlight some aspects. It's not very precise. I just want to highlight some limitations of the setting to motivate that there is a generalization of the setting which is called dynamical codes, which give some answers to these questions. Okay, which tries to circumvent these two problems in various ways. So let me explain what it means for a code to be dynamical. Everything was static so far. You have a Hilbert space, you chose a subspace, and that's it. Now where does the dynamics come in? No, the thing is, like, if you know, so if you get a measurement outcome -1, based on which operator measurement gave you a -1, you can already say which family of operators was the error, because if there is a family equivalence class of operators that anti-commutes with the operator that you measured, you got a -1, so you already know an equivalence class. Now among them you have to know which error actually happened. That is, now there are additional assumptions now. For example, if you have an error like this, you assume that this is more likely to happen than this is not in the example that I gave, but just consider some arbitrary code where this is an error. Suppose this is also an error. You say that this is less likely to happen than this, because this is, if the probability of happening this is p, then this is p square. So you say that multi-qubit errors are less likely to happen. So in the equivalence class of things that anti-commutes with the operator that you measured, you have to choose one cleverly. Like you have to make a guess as to what the error could be and then correct that. So that's a whole problem of decoding and really understanding which error actually happened. I will not go into that in this. Yeah, you act with the same operator again. It's all order 2, right? So you act with, in this case, you act with the same operator again. Yeah.
In this specific case, you cannot.
Yes. Yes. Yeah, this example is too simple to be able to correct anything. You can only detect this. You know which error happened. Yeah. You know an error happened in a family, but you cannot really correct it. Okay, so let me go to dynamical code now. So this is quantum error correcting code, dynamical code. So what do you do in this case? So here we saw that for error correction in static code, you keep measuring these operators, but it is the same set of operators that you measure at every time. You know, x, and z you measure at time t. You measure the same set of operators at time t plus 1, and you just go on. In particular, the operators that you measure at time t plus 1 commutes with the operator that you measure at time t, because you are measuring the same operators. Now you're going to change this. You're going to measure operators which doesn't commute. So at time t you measure some operators, at time t plus 1 you measure operators that do not commute with what you measure at time t. So I will not go to the general definition of a dynamical code. I will give you an example. Hopefully that makes it clear what it means. Okay, so there is one, so this is the measurement of some operators, and this if you measure two operators, you have also measured its product. So I can think of it as a subgroup of the poly group. What is the subgroup of operators that I measure? It is, so I have again 4 qubits, and the subgroup that I measure is this operator. So at time t1 I measure this operator. They commute with each other, so I can simultaneously measure them. So this is time t1. But at time t2 I measure another set of operator. Okay, this doesn't commute with this. So now the difference is that at the next time step I measure something that doesn't commute with what I measured earlier, and I just repeat this back to back. I measure this, measure this, I measure this, I measure this, just go on. At even time steps you measure this, at odd time steps you measure this. Now what is the benefit? The benefit is that you are only measuring 2 qubit operators. You are no longer measuring 4 qubit operators, and you can still do error correction with this, or error detection, let's say, with this, because there are still some equalities like this that you can get from this sequence. So let us find what is this. This is the detector, because it's called a detector because a violation of this detects an error. So in this case we have to find what is a detector from this sequence of measurements. Okay, questions on this? This is a very specific example. Okay, so what happens at time t1? At time t1 you measure these two, you go to a state which is some plus or minus 1 eigenstate of this operator and this operator, because you have measured them, right? So I can call the stabilizer group. So earlier I defined a subgroup, I chose a subgroup, and then I have a plus 1 eigenspace of that subgroup. Here I measure some operators and write down the subgroup based on the measurement. So an example is at time t plus 1 you measure z1, z2, z3, z4. The subgroup that stabilizes the states that you get is the following. Is it obvious that this group stabilizes the outcome that you get? So here O1, Z1, Z2 is the measurement outcome of Z1, Z2. So all I'm saying is that you measure Z1, Z2, if you get a plus 1 outcome, this is plus 1 times Z1, Z2, and I'm saying that the state is a plus 1 eigenstate of this operator. If you get a minus 1, the state is still a plus 1 eigenstate of minus of Z1, Z2. Similarly here. Okay, so by measuring these operators, I have gone into a subspace of the Hilbert space, which is in a plus 1 eigenstate of these operators, which depends on the measurement outcome. So now the subspace itself depends on the measurement that you did. Okay, I measured this. Now what happens when I measure t equals 2? T equals 2, when I measure these, yeah, I have questions. This is not 4 qubit because this is not an operator. This is O of 1, Z1, Z2. I just denote it as the measurement outcome of measuring Z1, Z2. So it's plus or minus 1 valued. So I am only measuring Z1, Z2, and I get some outcome. So I'm just multiplying this operator by a sign. Yeah.
That means that you still need to perform measurement on all 4 qubits.
That is okay. That is okay. The question is at a moment, is 2 qubits involved in a measurement or 4 qubits involved in a measurement? Initially I had z, 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 so all qubits were involved in a single measurement. Here I am still doing z1, z2, z3, z4 measurement. The outcome of that you can obtain from these outcomes, but individually I am doing only a 2 qubit measurement. I am first measuring 2 qubits and then I am measuring other 2 qubits.
Okay, so
Yeah.
you're going from 4 local to 2 local, but that's
4 local to 2 local, but indeed the crucial point is that the product of these outcomes will also give you the measurement outcome of the 4 qubit measurement, right? Z1, Z2, Z3, Z4 outcome is also fixed by the product of these outcomes. But here you are doing low number of qubits are involved in the measurement sequence. Yeah. Here I am not describing anything non-local yet. So these are, I don't even have a lattice here. So, but the usual examples are still local. So you don't maybe have one. That's probably a way to overcome locality. So if you have this LDPC, Floquet version of quantum LDPC codes, you would need that, I guess, still, because you still have some known locality. So you still need to do like 2 qubit measurements, but those qubits are far away. Yeah. But here I don't even have a lattice. It's like an abstract description of like a simple example. Okay, so I measured this. I got this group, which is the +1, which defines for me the +1 eigenspace where the outcome state is lying. Now I measure this. When I measure this, for example, I measure x1, x3. x1, x3 doesn't commute with z1, z2. So the value of z1, z2 is not fixed anymore. So the outcome that I get, I don't know which eigenstate it is of z1, z2. So when I measure this, the way you should think about is that you get a new group S2. Okay, I measure x1, x3, so it contains the measurement outcome of x1, x3. So the operator that similar to what you wrote down here you write down the measurement outcome of x1, x3 times x1, x3. Similarly, the measurement outcome of x2, x4 times x2, x4. Okay, so far so good. But there is one more term in this group, because this operator doesn't commute with this operator doesn't commute with this, but the product commutes with these two, right? So the product always commutes with these two, so the product still survives in the group that I have, z1, z2, O1, z3, z4, z1, z2, z3, z4. This is the new group, because you kicked out this guy and added x1, x3, because this doesn't commute with this. You kicked out this and added x2, x4, but the product commutes with these two, so that remains. So when you update these groups, you have to make sure which one commutes and which one doesn't commute. So now you see, you started with a group which has 2 generators. Now you have a group with 3 generators, because you have this, this and this. So you have increased the size of your group by doing this measurement. Yeah. Yeah, I'm not combining, I'm not calling it O1 of z1, z2, z3, z4, because I'm never measuring that 4 qubit operator. I only know these outcomes and I just take a product to get. It is equivalent, but it's just that I don't have access to O1 of the product because I'm never doing that measurement. That's the whole point of this, because in the static code I was getting O1 of the product directly because I was doing that measurement. Here I have to compute the O1 of this using the product of O1 of these individual measurements. Mathematically is the same, indeed, mathematically is the same. Yeah. So you get this. So when you start measuring operators that do not commute with each other, this group starts increasing in size, and this is a bad news, because this group, if it keeps increasing in size, the +1 eigenspace of this group will just become one dimensional, which is not good, because then you don't have a logical qubit anymore. But as we will see, this group size will not increase anymore. This is as big as it gets. So you started with 4 qubits. This group has 3 generators. So the +1 eigenspace of this group turns out to be 2-dimensional. So you still have 1 qubit remaining, logical qubit remaining in your code. When you do the next measurement, the size of this group will not increase. Let's see that. What is the, you measured this, you have this, you measured this, you have this. Now you measure this again, okay? So S3. Now you measure these guys, Z1, Z2, Z3, Z4. So as usual, we have this. So now I am measuring at time 3. So I have O3 of Z1, Z2, of Z1, Z2, O3 of Z3, Z4, Z3, Z4. And again, the product of these two survives. The product of these two commutes with these measurements. So I still have the product here, O2 of x1, x3, O2 of x2, x4 times x1, x2, x3, x4. This is the third group that I get. So you see, you don't increase the size of the group anymore. You kick out some elements, you added some elements, but the number of things that you kicked out is the same as the number of new outcomes that you get. So it still remains as a 3-generator group. And you keep repeating this measurement sequence, the group will flip between these two. That's it. It will go S2, S3, S2, S3 like that. It will just repeat. So that means that at some point the size of the group stabilizes. Yeah. I just went back and forth. So M1 is this, M2 is this, M3 is this again. So at each odd time step I measure this, at each even time step I measure this. Yeah. Size of the group? Yeah, so it depends on the measurement sequence. So here I have chosen a particular sequence so that the size just becomes, some 3-generator and then stabilizes there. But if I choose a sequence of measurements arbitrarily, the size of the group will keep on increasing and become the maximal abelian subgroup of the polygroup, where the one-dimensional, you just get a one-dimensional logical space. You never want to reach there, let's say. So you have to choose the measurement sequence carefully now, so that this doesn't just go on increasing. In this example, once you reach here, you just get these two back to back. Okay, so what do we learn from this? So we measured, so we can see that we measured Z1, Z2, Z3, Z4. So the outcome of this product is fixed. You have a particular outcome, this is given by this product. Now you measured Z1, Z2, Z3, Z4 again, right? The third time step. This product should be the same as the outcome that you got at the first time step, because you already measured Z1, Z2, Z3, Z4. So you measured Z1, Z2 and Z3, Z4 individually at time step 1. So you know the measurement outcome of this product. At time t equals 3, you again measure Z1, Z2 and Z3, Z4. Their individual signs are not fixed, but the product should be fixed because you already measured it and it was always commuting with everything. So you never go outside the +1 eigenspace in a way of this operator. So we had this equation here, which is the detector. What is now the detecting equation in this case? Now everything is dynamic, changing with time. So, but you can still write down a detecting equation. What is that? So at time t, you measure Z1, Z2. Z1, Z2, yeah. At time t, you measure Z3, Z4. This should agree with time t plus 2 of Z1, Z2. Why is it t plus 2? Because at time t I measure Z1, Z2, Z3, Z4. Time t plus 1 I am not measuring z's, I am measuring x. Then at time t plus 2 I am measuring z's again. And this product should agree with this product, even though individually these signs are completely random. Similarly, I have the same for the x's. this is the detecting equation now. And now you can see that this is only valid when t is odd. So this is for t odd, and this is for t even, because for t even is when you measure these, and t odd is when you measure these. So your detector now changes with time. Earlier you just had this equation valid for all time, because you were not doing this more complicated thing of measuring non-commuting operators. Now you measure non-commuting operators, so the equation that you need to satisfy changes with whether the time is odd or even. Now a violation of these equations will detect an error. If there is some error that violates any of these equations, this is the ideal world, right? You measure, you get the outcome, everything is good. If there is an error, it will violate one of these equations, and then you know there's an error. But the detector is changing with time, so now it's not just which error happened, but when it happened matters now. Because in a more general setting, even more complicated example, these detectors will change drastically with time, and at particular time you have an error that violates one of these, but in another time you may have an error that doesn't violate it. So because the detector itself is changing with time, you need to have a space-time picture of an error. It's not when or where it happens, it's not just where it happens, it also matters when it happens. So error correction becomes more complicated when you have these dynamical codes. So the advantage was you only have to do 2 qubit measurements now, but what is the complication now? You have to have these time dependent detectors, and the errors that you can correct will depend on time.
So you only detect them after 2 time steps, right?
Yeah, so it's like this in this window. Yeah, so you have to, so here I'm having a lot of assumptions that you just have an error and nothing happens to it, and I'm assuming that these measurement outcomes are, like basically if there is no error, I'm assuming that these measurement outcomes themselves are error free, things like that. So indeed, if an error happens as a unitary operator on some qubit, I can measure it, I can detect it in this time window t to t+2. Before or after that, I don't know. Yeah, so it's like these time windows, I keep measuring these, but this is part of the code. This is not something that you do extra. This is how you define the code. The subspace is defined by this sequence of measurement processes. So this is part of defining the code, but that also does some error detection for you. You just keep measuring this and checking. Yeah. Okay, so nowadays, so let me just give you a more well-known name for this. These are Floquet codes, because there is a periodicity in the measurement sequence. You measure M1, M2, M1, M2 go on. If you necessarily don't need a periodicity, then it will be a general dynamic code. And Floquet codes, people are studying all kinds of Floquet codes now, trying to understand them. There is a Floquet version of the toric code, which I will not study here, called the Hastings-Haar code, and that is more complicated than this one, because here I measured x1, x2, x3, x4 independently, but what did I lose? In the original toric code, this XXXZZZ, I had 2 qubits in the logical subspace. Here I only have 1 qubit, because this group has 3 generators. So okay, I made the measurement easier by going into this 2 qubit, but I lost a qubit in the process. So this is not the best way to make things dynamical, but I'm giving this example because it's the simplest setting to explain this. So yeah, there is a preference in the sense that maybe you want even though the logical subspace is changing with time, you still want to stabilize it. You still want to say that that logical subspace has a given dimension and that dimension doesn't change, let's say. If you prefer that, maybe Floquet will help, because you're just doing periodically a set of measurements. At some point your logical space is of a given dimension and the dimension doesn't increase. If you start doing things that are not periodic, maybe you may have to be more careful to kind of fix the dimension of the logical subspace. Maybe you don't even want to fix the dimension of the logical subspace. That is another situation. Yeah. Yeah.
So if you have a dynamic code like this, projecting the states of these new logical
Yeah.
subspaces, is there any problem in are there no problems putting an algorithm on putting gates, because you lose any control of what
Yeah, so now what the logicals we initially defined as things that commute with the stabilizer group, but now the stabilizer group is changing with time, so the logicals will change with time also, because they are the ones that commute with a given stabilizer group at a given time, but at a new time the stabilizer group is new, so the logical is also new. So logicals also change with time. I don't know about actually implementing this in an actual explicit algorithm, but people are studying logical operations that you can do in Flow-K codes. Yeah, and there are some automorphisms or logicals that you can implement more natively also. By just a sequence of measurements can itself give you a unit tree. That's those kind of things can also happen in Flow-K codes, but I don't want to go into logicals too much. Yeah. Okay. So so this is that. So where is non-invertible symmetries in all this? It was more like a QI talk. But anyway, so okay. So the question that one has in this is that for usual static codes there is a TQFT or field theory understanding of a static code, because in a static code, as I explained, you can think of it as ground states of some lattice model, gapped lattice model, and things like excitations. What are the errors? Errors correspond to excitations, and they correspond to anions in the gapped model, and they are labeled by line operators in some Chern-Simons theory or some TQFT. So there are various aspects of the code that you can detect in the IR itself. So the question is, for these dynamical codes, do you have an IR understanding of these dynamical codes? And is there a way to understand this error correction process as a process in the IR TQFT? That is a question. And does it help you with something, this understanding? Okay. So that is the main question that we would like to understand. So I will describe what I will do. I will give the upshot first, because the time is already quite. So I'll give the upshot so that you know what is the punchline. Then I will go to the details. Okay, what is the upshot? The upshot is that measurements these involve a choice of measurement. So given measurement, I will relate it to a non-invertible symmetry. So you should think about this is a zero form symmetry. So you should think about this as a topological defect labeled by this measurement. I will tell you what the map is, but for a given measurement, I will give you some codimension 1 topological operator that acts on the other operators of your theory. Yeah, so this will be obtained by this condensation. So it will, by construction, this will turn out to be a projector basically, and I want it to be a projector also because measurement affects the other operators in your system. You can ask, under a measurement, does another operator remain in the stabilizer group or does it get kicked out? This is basically answering, can I pass an operator through this defect or not? So basically I will relate the measurement process to the action of this operator on the other operators in your theory. So any given measurement, I will write down a non-invertible codimension 1 operator acting on your theory. What if you have a sequence of measurements? You have a sequence of measurements like you have here. This just corresponds to a sequence of these defects acting one after the other. So I will just call it M1, M2, M3, etc. Okay, so there's a sequence of these defects. So each measurement is a particular topological defect. A sequence of measurements is a sequence of topological defects. But once you are in the world of topological defects, you can just fuse all of this into a single operator. Okay, so from this, I will consider. So once you give me a sequence of measurements at a particular time frame, from T1 to T2, I do this bunch of measurements. I write down the corresponding operators and I squeeze it to a single operator. And now this is how you make the dynamic process of error correction into a static problem, in the sense that here you had these sequence of operators corresponding to the different time steps of measurements. Now you have, these are topological, so you squeeze it into a single operator. Now the error detection process translates into some properties of this operator. Yeah. Yeah. They do not commute. Yeah.
And if they use something, if they not commuting, so they probably interact with each other. I mean, they use the same.
Yeah, so it's like, so I'm fusing literally like, so in the case of invertible symmetries, I can still consider like 2 plus 1D, let's say these will be surface operators labeling some non-abelian group, but I still fuse them by just taking a corresponding to taking a product of the group elements. So I just mean that fusion. So it may not be commutative, but I can still fuse to create an operator out of it. But the way I fuse matters. I cannot take one around the other and then fuse like this. The order matters, but still I just fuse. Yeah, yeah. So this sequence tells me what sequence of operators to consider, and then I squeeze. Now, okay. So this is, and error correction will be the following. So this operator here, I've drawn it as a surface operator. Really, this whole thing will be in 5 dimensions. Okay, which is 4 plus 1 dimensions, and the reason is that I can do this in 2 plus 1D itself, but I will have to restrict myself to qubits. If I am restricting myself to qubits, more or less I can do this in 2 plus 1D itself, but 5D you naturally have a set of operators which have an antisymmetric braiding. Surface operators in 5D braid antisymmetrically, and that directly translates to the fact that the Pauli group has an antisymmetric commutation relation. Yeah, because here I will relate braiding of some operators to commutation relation of Pauli's. In 2 plus 1D, the corresponding thing will be line operators braiding, but the line operators braiding is symmetric. So if you have mod 2, it's okay, but if you go to mod 3, then you can't do it. So just to be general, to include qubits and more general codes, I'm going to 5D. Even though I'm drawing it as surfaces, these are actually 4-dimensional operators. These are zero-form symmetries. So 4-dimensional operators acting on surface operators. But these are all, because these are all hard to draw, I will think about these surfaces as the 4-dimensional operators. And in the 5D theory, I have surfaces which I will draw as lines just to depict it. So basically, I have a line coming here and passing through these defects. Okay. So this is actually a surface operator. This is actually a 4-dimensional operator. But I cannot draw it, that's why I'm drawing it like this. Or this picture is exact if you are in 2 plus 1D and if you are only dealing with qubits. Okay. Now this line is a general Pauli operator. Whether there's an error or not depends on what happens to the line when you try to pass it through these defects. Okay. So
I don't
yeah.
have that dimension. So
Yeah.
why you can get in 2 plus 1 when you have to go to 4 plus 1?
Yeah, I will explain it in the next step. Yeah. So just to highlight, because it's already 1 hour plus something, I will just say that detectors, this kind of detectors, you can topologically map it to the following problem. You try to find the action of these surfaces on lines, which is actually the action of 4-dimensional operators on surface operators. You try to pass them through these defects. You can sometimes get configurations like this. You have the trivial line here, and you have the trivial line here. That means that this line can end here and here. So it's a junction to the trivial line. What happens when you have a junction like this to the trivial line? You have a line segment now. When you squash this into this operator, this line becomes a point. That's okay. So remember that this is actually a surface operator. So when you squash it, it becomes a line, but here I am drawing it as a line becoming a point. So whenever you have some line operator that can end on 2 sides, when you squash this, it becomes a point. Okay. These are the detectors of the code. So every time the dynamical code has a detector, you can map it to a line that can end on either side, and it becomes a point on this fused operator. What is an error? An error is a line that tries to pass through these defects but gets stuck in one of these defects. It cannot pass through, because you will know from the action of these surface operators. When the surface operators, these are non-invertible surfaces, so every line cannot pass through these operator. There are some lines which just get stuck on the surface operator. What happens when you have something like this and squash this? It will become a line operator on this squashed operator, and in this case there is a linking between a point and a line, and this linking is the error detection process. An error is a line, a detector is a point, and the linking between them is the error detection process. This is all in 5D. So what's going on? These are 4-dimensional, these are 2-dimensional. If you have a surface operator that can end, you squash it. This is a line, this is a surface. It's a surface, is a line braiding in 4D. They can braid non-trivially in 4D. If there is a non-trivial linking, that is an error detection process. So yeah.
It's for with like a sheet attached, like whatever higher dimensional sheet.
Yeah, that's right. So you can still imagine that. So here I was simplifying it as a vertical line. You can keep track of the sheet if you want.
But I guess what I'm wondering is, like, if you keep track of that sheet, and it ends up depositing some line segment on M3, and then you collapse it.
That's right. So still, yeah. That's because an error here could still be an error here. It may anti-commute with both M2 and M3.
But I guess what I'm wondering is, with collapsing procedure, can
Yeah.
those arms cancel out?
Sometimes they do cancel out. Yes. Yeah. That's why in this operator here, there are some configuration which will become the trivial operator here. Yeah. It's not a problem in the sense that if an error occurs twice and if it's an order 2 error, it's okay. Yeah. So there is a lot of redundancy. So the map from the operators here and the operators on this operator is not 1-to-1. There are many configurations which become the same configuration on this operator once you squeeze. But that is okay, because those are all cases which are like you can quotient out by. Yeah. Okay, so this is the upshot because it's already time. Let me explain finally what this theory is. So that will be the final thing. So this would be the topological understanding of this error detection process, because every measurement is a non-invertible symmetry, and when you pass operators through it, this is like computing the stabilizer group. In the stabilizer group is computed by understanding what happens to a Pauli operator when you do some measurement. Here, when you pass these operators through these defects, it's like computing this instantaneous stabilizer group. Some things get stuck on the surface, some things can go through. Then a line that can go through all the way is a logical. A line that can end is a detector, like a stabilizer. A line that gets stuck is an error. That is the main point. Okay. So what is the theory? This is the final thing I will do. So I'm in 4+1D. What is the theory I'm dealing with? I'm dealing with a 2-form gauge theory. Yeah, so I'm purely in the IR now. Even my physicals are given by something is in the IR. So lattice is not may not be the most useful thing to introduce at this point, because usually in the lattice the physical qubits are on the lattice and the logicals are just what you preserve in the IR. Here both physical and logicals are in the IR itself. So yeah, it has benefits, like because you can visualize everything topologically, but the thing that you lose is locality. So okay, so this is the model that I have, and these BIs are 2-form U1 gauge fields. So it's very similar to the K matrix of an abelian Chern-Simons theory in 2+1D, but here now there's a crucial difference. The crucial difference is that this coupling matrix should again be an integer matrix for this to be gauge invariant, similar to Chern-Simons. However, in Chern-Simons theory, when you flip these two, you do not get a minus sign. So this matrix should be symmetric in Chern-Simons theory. But these are two forms. So when you do integration by parts, you get a minus, crucial minus sign. Therefore, Kij is a antisymmetric non-degenerate matrix, integer matrix. I guess positive integer matrix. So, so this antisymmetric nature has a crucial consequence for the operators in this theory compared to Chern-Simons theory. Because what are the operators in this theory? These are, so for a given 2 manifold, let me just call it sigma, I can take this gauge field and integrate it over this 2 manifold. So let me actually write it more clearly as something like AI bi with some summation here. And so AI is basically, it depends on the number of gauge fields I have, just write it as some z to the n. So there is some word vector that labels the gauge fields, and I integrate the 2 forms over a 2 manifold, and I get a surface operator out of this. Okay, these are the natural operators that I have in the theory compared to the line operators in Chern-Simons theory. These operators have a braiding. So there's a braiding for 2 such. So let me label this with this vector, that is this AI. There's a braiding for these surface operators now, because these are 2-dimensional operators, and this is very similar to what happens in Chern-Simons theory, but you have the coupling matrix shows up in the braiding exactly like Chern-Simons theory, but this matrix is antisymmetric, not symmetric. So the braiding of surfaces is antisymmetric. Now why do I need this? Because I want to think about these surface operators as corresponding to polymatrices, and polymatrices have an antisymmetric braiding, and that is going to come from the antisymmetric matrix K here. So this is the last part. I'll just write down the K. So if I choose like K to be, so this is the simplest case where I choose K to be some like a case of qubits, right? I choose K to be this block diagonal matrix where I just have 0 2 2 0 0 2 2 0 and go on, and then I consider the case where like I have so basically I want, so the fusion group of the surface operators will be just some Z2s, and the braiding will give me the anti-commutation relation between the surface operators, that is exactly like the polygroup. So but this is for a particular choice of K, I can choose K to be more general, and then I will get like qubits, qudits, qtrits, like a combination of composite system. So depending on what you choose K to be, this fusion group of surfaces will be it's like a general abelian group, like a product of Zns. As long as there is a antisymmetric form on it, it can be any abelian group basically, and that is related to a polygroup acting on some qubits. So the isomorphism is between polygroup elements and surface operators in this theory, where the braiding gives you the commutation relation of the polygroups. Now you have a interpretation for measurements, because a measurement corresponds to a set of commuting poly operators that corresponds to a set of surface operators which doesn't have an anomaly, because this beta is a mixed anomaly for this symmetry. It's a braiding. Which surfaces can you gauge? The surfaces for a subgroup for which beta is trivial, you can gauge it, because that's a non-anomalous subgroup. That precisely corresponds to commuting poly operators. So poly operators gives you surface operators, commuting polys gives you a subgroup that can be gauged. This is enough. Yeah.
Now assign sigma of your four-dimensional space, and then that's what you utilize on.
Yeah, you can think of it that way. Yes, indeed. Yes,
it's like finitely many.
there's a finite many cycles. So depending on how many gauge fields I choose, that fixes the physical qubits for me. Yeah. So this particular non-invertible symmetry is obtained in the following way. I choose this TQFT. I obtain a new TQFT by gauging a non-anomalous subgroup of this symmetry, but I only gauge it in a particular slab. So I take this TQFT and I gauge the symmetry in a particular slab, and I fuse this. This gives me a operator corresponding to this B. So this is like an operator corresponding to this B from T to T. So I choose a subgroup of this group which I can gauge. I gauge it only on this in this strip, and I fuse the interfaces to get an operator. This operator is non-invertible because gauging is a non-invertible process. You kill some operators when you gauge. This is how you create these operators here. Yeah. B is not Lagrangian. Yeah. So it's not maximally gauging everything away. A set of polys that commute with each other corresponds to a symmetry that you can gauge. You use the gauging process to create this operator, these M operators here. So that is how every measurable set of operators corresponds to a non-invertible symmetry. And you have to go through a bit more work to kind of reproduce this, but I just want to give an upshot as to. These are all codimension 1 because they are obtained by a interface between a theory and another theory. So this is an interface I, let me call it, and this is like I dagger between the gauge theory and back to the original theory, and B is like composition of them. So I and I dagger are codimension 1, so B is also codimension 1. That will play a role when one has to study logical gates of this model. So the zero form symmetries of the two form gauge theory should correspond to logical gates of the dynamical code. It is something that we are exploring now, but we haven't. Yeah. Yeah. So if you have an invertible thing here, it will be basically giving you a condensation defect up to a invertible operation. Yeah. So that you can think of it as a measurement and a logical operation. Yeah. Here I just focus on pure measurements, so I'm doing just pure condensation. Yeah, pure gauging. So yeah, so the upshot is you have measurements corresponding to some non-invertible symmetries, and this is the particular way of creating them. And the fusion gives you a super operator, like you just fuse all of them to give a single operator. And the braiding of operators on that single defect is the error detection process, even though I didn't explain all the details. And this is how you make a process that is dynamic because it depends on the time steps. But once you fuse it, it's at a given time because this time doesn't matter in the topological theory, and you make it a static problem about whether two operators braid or not. Whether two operators braid or not is not a time dependent statement. It's just a statement about the linking. And that is how you map a dynamic problem to a static problem. Okay, maybe we'll stop here. Thanks.
Is basically what we studied earlier, and we just identify it as measurement. That we just make it table values.
Yeah, so the only reason I'm calling it a measurement is because a measurement, a simultaneously measurable operators is a subgroup of the polygroup which commute. So it's an abelian subgroup of the polygroup. Yeah, because abelian subgroup corresponds to a subgroup of the symmetry, the surfaces for which beta vanishes. Because commutation relation comes from beta. So that is why it exactly corresponds to gaugeable symmetries. And once you have a gaugeable symmetry, you can create this operator from it. Yeah. Error correction is never discussed in the paper also, because it's another can of worms. But you can characterize which errors gives which syndromes, like which measurement outcome, using this braiding. Like which equivalence class of errors gives you which. So this defect is 4D. So the braiding is between a line and a surface in 4D, yeah, which can be non-trivial.